Alright, Chapter 12, Part 1B. Apparently we had the last couple of slides from Chapter 12, Part 1, that there was a video issue, so we're going to re-record those last few slides with you here, and so we'll continue where we left off. Okay, so from the chart on page 290 in your textbook, the table 12-2, selected abbreviations used in medication administration. The big ones on here, IV, I think is pretty well known, intravenous. IVP, intravenous push, also sometimes referred to as intravenous bolus. We'll kind of use those interchangeably, but this is an instance in which you would be giving a medication. You put the needle through the injection port, give them X amount of the syringe worth of medication, and then continue to flow your IV in. So IVP or IV bolus. kg for kilogram, KO not typically used. KVO and TKO commonly used for to keep open or keep vein open, very small amount, roughly 30 mils an hour. Capital L is for liter. MCG and MG, two units of measure, could easily be confused, but commit to memory a microgram is MCG and a milligram is MG. Milligram is 1,000 pieces of a gram, and a microgram is 1,000,000 pieces of a gram. There's another symbol that sometimes gets used for microgram. It's an older symbol that is kind of fallen out of favor, although it still died hard with me, but the symbol looks something like a weird looking U like this, a little tail in the front, and then G. So it's this tail on the front of this U is another way to say microgram. So it's a front-tailed U. And then of course the milligram is just mg. So commit to memory the little difference there. MIN for minute, little m big L for milliliter, which is common, very commonly used abbreviation for us. NKA is no known allergies. NKDA, or sometimes NKMA, for no known drug allergies or no known medication allergies. NKA a little more global, when you can say things like foods and environmental allergies, bites and stings and whatnot, whereas NKDA or MA would be used specifically to medications or drugs. So, go back to normal. There we go. Okay. Capital NTG is nitroglycerin, and it goes commonly with capital ASA, which was back on the first slide, which is aspirin. So very commonly used. P with a line over it for after. It's kind of falling out of favor. PO, or per os, is for by mouth. PRN is as necessary. It's fairly common. Q, kind of also falling out of favor for every. Q's and P's can kind of be confused. I think that's why that's kind of going away. RX for treatment. You see that commonly on prescription pads, sometimes drugstores and whatnot. An S with a line over it for without. So the C with the line over it for with, S with the line over it for without. Sub-Q, sub-CUT, SC, SQ all get used for subcutaneous or type of injection that we're going to cover. Stat, if you've ever seen any medical show ever, you've heard stat, for statin or immediate. SVN, not terribly common, and TKO we've already covered. So we'll dispel that myth that you heard that once you complete algebra in school you will never ever use it for anything in real life. Well, this is where that becomes false. We use algebra for the mathematical calculation of drug dosages. The good thing about it is we use the metric system which is a base 10 system, so it's very easy to move back and forth within a base 10 system, unlike that of our current English or imperial units, which is kind of willy-nilly, where it's 12 inches to a foot or 16 ounces to a pound, or 132 ounces to a gallon. So where there's not that consistency within the imperial system, the metric system uses base 10. So it's 10, 1 up, 10, 1 down. Science and medicine use this exclusively throughout the world, whereas the U.S. and United Kingdom have not been so quick to jump on the metric system. And so we still use the imperial system in our everyday life, but we exclusively use metric within our work. So this is going to show you 3 of the 4 major units from the metric system that we use in medicine. Gram for mass, which is lowercase g, liter for volume, which is an uppercase L, meter for length, which is lowercase m, and the missing one is capital C for centigrade or Celsius for the metric unit of measure for temperature. So mass or weight is gram, and if I were to take, and we'll draw on the screen again here, take my highlighter and just write down through there, that is where you need to keep in mind that the base unit actually falls. So in the case of kilogram there, right to the left now in the yellow highlighted bar, that is where gram would fall, or liter or meter, depending on what you're using. Understanding that you go 1,000 upwards from the base unit to hit kilo, and 1,000 downward to go to milli, and another 1,000 downward from milli to micro, or a total of 1,000,000 downward from base unit to micro. So the really commonly used prefixes and divisions are shown here. And so when we take a look at these, kilo is really about the only time we really use kilo in our practice is in grams. So kilograms, we measure patient's body weight in kilograms. Otherwise, we will be using the base unit gram, or milligram, or microgram. For volume, we use liter, and we use milliliter in most cases. We don't usually use other divisions or subdivisions very often, with the exception of maybe when you're taking a blood sugar. Your reading is going to come out in a milligrams per deciliter, D-E-C-I liter, or lowercase d liter. And that is a tenth. So it would be between the base unit and the centi would be the deci. So milliliter and liter are commonly used. Millimeter, centimeter, and occasionally meter get used for length. We'll measure patient's height in meter. And then centimeters and millimeters would be more commonly used for describing maybe the size of a wound or its location in comparison to a landmark upon the body. There's an interesting coincidence that occurs with these 3 units, and at a certain temperature, and I believe it's room temperature, or maybe it's just above freezing. I'll have to look that one up, but there's a certain temperature in which 1 milliliter of water, and it's at sea level, 1 milliliter of water at a certain temperature weighs 1 gram and is 1 cubic centimeter in size. So interesting coincidence there. But actually it's probably not a coincidence, they probably figured it that way. But so you often hear about cc's, and a cc, a cubic centimeter, think about a container that's the size of a standard sugar cube. That 1 centimeter tall by 1 centimeter deep by 1 centimeter wide container, if it were open, you would be able to put 1 milliliter of fluid into that. So mLs and cc's often get used interchangeably. So we use prefixes for multiples and subs of our various units. Like I said, a kilo versus a gram versus a milli versus a micro. That's just different ways of measuring the same thing. It's like if we say, what is that? Is that 12 inches or is it a foot long? Well, it's the same thing. It's just a matter of which unit you chose to use with it. So this is just the same unit, just assigning a prefix to it to give it a different meaning. So it's basically like saying to the 10th power, to the 100th, to the 1000th power, whatever. So these prefixes that we've talked about, the kilos, centis, millis, there are others. Decis for tenths of, decas for 10 times, hepta for 100 times. We got centi for hundredths. We can even go down to picos and nanos, which are itty bitty, micro, tiny, little, ridiculously small. We can go up to megas, which are million times larger. So whole numbers get left in place to the left of the decimal. So if we're talking about 1, it would be 1, that's it, not 1.0. But fractions, on the other hand, they get a leading 0, and they are to the right of the decimal. So if we're saying a tenth in decimal is 0.1. Always, always, always get that leading decimal there. I'm sorry, leading 0 in front of the decimal there. That helps draw attention to that decimal. So it helps us say, oh, there's not supposed to be zeros out in front of whole numbers. So let's look at that again. Oh yeah, there's the decimal. So it's 0.1 milliliter of fluid. The reason we don't use a decimal and a trailing 0 for a whole number, such as 1.0, the reason we don't do that is because you can easily miss that decimal. So if you missed the decimal and it was 1.0, you maybe would give the patient actually 10 instead of 1.0. So always, always, always a leading 0, never, never, never a trailing 0. So drug dosage calcs, when we talk about some customary or some a lot of times referred to as kitchen measurements, household measurements, we have a couple things we can take for their equivalents. So tablespoons and teaspoons often get used in over-the-counter syrups and whatnot for cough syrup. And so remember that it's 3 teaspoons to a tablespoon. A teaspoon is 5 mils, so a tablespoon is 15 mils. A fluid ounce is 30 milliliters, or 2 tablespoons. Or then that would be 6 teaspoons to a fluid ounce. A quart, 950 milliliters, just a hair shy of a liter. And then a gallon would be 4 quarts, which is 4 times 950 is 3,800, 3.8 liters. 1 inch is 2.54 centimeters, so it's just a hair over 2.5 centimeters in length. And a pound is 0.45 kilos. Most of the time we remember it the other way, though, which they have in parentheses there. 1 kilo is 2.2 pounds. I used to like to say that I had the most perfect weight for a patient, that you would have to convert their pounds to kilos, because I used to weigh right at 220 pounds. Divide 220 pounds by 2.2, it comes out a nice clean even 100 kilograms. So 220 is 100 kilos, 440 is 200 kilos, heaven forbid 660 be 300 kilos. Now there's a quick way to do the kilo conversion. and we call it the 2 a.m. rule. So if you take a person's weight in pounds and you cut it in half, so let's take that 220 again. 220, cut it in half, that's 110. If you subtract 10%, which is 11, or in this case, that 110, 10%, you can just lop off that last zero and it gives you 10%. So from 110, we subtract 11. And when we do that, we have 99. So a rough guesstimate that we get for the 2 a.m. rule is a 220-pound person is 99 kilograms. So, which is close. We know that doing it mathematically, it's 100. But 1 kilo off for that quick rule, if you're having a hard time doing the actual long math in your head, is pretty stinking close. Of course, we will take accuracy anytime we can get it, but sometimes we have to just kind of shoot from the hip. So basic calculations. To find the amount of drug to administer when given a physician's order and a concentration of the drug available. So what we need to know is how much does the doc want us to give, or the protocol want us to give, and how much do we have in our hand in that package. So the true calculation is how much of what we have are we supposed to put in the patient. So we're going to use fractions to basically get the information that we're looking for. So we might have to use a little bit of reducing, might do some cross multiplying, some dividing to ascertain that information. Take for just a moment and think about what I'm going to say. So stop writing, stop looking, just kind of imagine. We are talking about usually such incredibly small amounts of a substance, of a medication, that we can't maybe even see it. In most cases we don't. Because a lot of our drugs we're giving milligrams worth. Well, the weight of a gram is roughly that of a United States dime. It's pretty close to a gram. So if you can imagine taking a US dime and cutting it into 1,000 pieces, it's going to be hard to see 1,000 pieces of an itty-bitty little US dime. Remember, most of our substances we're giving aren't hard metals like the nickel, the nickel and the copper that our U.S. coins are made out of. We're actually talking about powdered substances that are going to be even smaller. So imagine cutting these items into 1,000 pieces for milligrams, or 1,000,000 pieces for micrograms. We have to put it into something to be able to give them something tangible, because we can't just take a microscope and pick up a milligram of this and put it into a patient's blood. So the tangible thing, the matrix, if you will, the suspension. Now don't confuse the term for suspension that I'm using for illustrative purposes here. Don't confuse that for the actual suspension that we have some syrups and cough syrups made in. But we have to put it into something that's big enough for us to give. And in this case, think about an oily Italian salad dressing. Okay, when you get that Italian salad dressing, you stir it up or you shake it up, and that disperses all those spices and peppers and onions and whatnot all throughout the liquid. And we have to think about the liquids that we're putting into somebody's vein or into their mouth or whatever to be a kind of a suspension like that. And that's why we have to come up with a tangible item of the amount of fluid to give them, or the number of pills to give them. Now understand, when you're giving somebody a pill like an aspirin, that aspirin isn't necessarily 81 milligrams or 325 milligrams, whatever, of aspirin pressed into one solid chunk. It's probably a little bit of that aspirin mixed in with some other substance. We'll just say, let's pretend it's a crushed up chalky candy like a sweet tart or something. That's kind of the matrix. It's kind of the holder of that. So what we're actually giving them is usually much less than what we actually are are seeing in our hand or our syringe. Weight-based dosage calcs. This is a dosage based on the patient's body weight. This is very common for our pediatric patients. The patient's weight is always taken in kilograms, almost always, and then we just divide their weight in pound by 2.2. So our weight-based dosage calcs, we're not good at guesstimating, so I would suggest you talk to your patients. Tell them, hey, in confidence, I know that this is a touchy subject, but in confidence I need to know how much you weigh accurately. Because if I have to give you a medication, I need to know if I'm giving you too much or too little, and it's going to be based off of how much you weigh. If you want to try this for fun, then try guesstimating people's weights at home that you don't know for sure how close they are. If you've been tracking this for their entire life, then that's not going to be a fair guesstimate. But people that you maybe don't know, try guesstimating it and then have them step on the scale and find out how close you are. And we are notoriously terrible at it. So it's best to use that. Otherwise, using a linked-based resuscitation tape, something gets called the Broslow tape or the Brosel-Hinkle system, where it is a tape that you measure from the top of their head to the bottom of their feet. And it gives you a rough guesstimate of their body weight. Okay, this picture you will find in your textbook on 294. What I want to draw your attention to is down towards the bottom middle of this picture. You see I'm referring to the drip set or drip chamber, and you have micro drop and macro drop. Micro drop is a little steel needle, tiny little drops come out of it, and a macro drip or macro drop set has a large plastic tube or orifice that makes big drops. Now, what? Well, when we're looking at this, look at the bottom line on this slide. The macro drops are 10, 15, or 20 drops per milliliter. The micro drop, which is not on this slide, is 60 drops per milliliter. So it all ends up being the same. It's just how easily, how fast, how quick can you get there. And so it's easier to count 10 big drops than it is 60 little drops. And you can move liquid so much faster with the big macro drops than you can the micro drops. So if you needed to put 1,000 milliliters of fluid into a person, and you cranked both the macro drop up and the micro drop up, you would probably have only at best a quarter of that micro drop bag in when the whole macro drop bag was completely infused. So it's a matter of what are you intending to do. Most of the time we use a macro drop, which is illustrated here, that bottom line, to give most fluids to patients. If we need to be very, very, very precise and make sure they only get a very precise amount of fluid, we would use the micro drop. And usually when we're doing a medication infusion, so they get medication through their IV constantly, we would use the micro drop set. So basically what we're referring to, remember when we're talking about a drip set, is how many drops in varying sizes does it take to make 1 milliliter of IV fluid. So we're going to check time in which we're supposed to give our IVs over as well, and that time is almost always measured in minutes. We're not going to sit for an hour and watch every time it drops. We're going to sit for a minute and watch every time that it drops, and know that if we multiply that by 60, that's going to give us the amount of fluid over an hour. Remember I said TKO and KVO is roughly 30 mils an hour. And our weight-based IV drip calculations are not very common, except for maybe in the pediatric population. We're perhaps going to give them X amount of fluid over X amount of time, or in the cases of pediatric IV fluid resuscitation, we usually give 20 milliliters per kilogram. So that's going to say how much are we going to need to give them over a certain amount of time. So that's a weight-based calculation. So we have to do kilos. Drug dosage calculation with an IV pump can be a breeze. This is probably the most commonly used portable IV pump used in field EMS today. and this is actually a 3-channel pump. You can see just how small it is. You can run 3 different fluids through this at the same time. The real beauty about this is, number one, it's extremely precise in the amount of fluid that it gives. And another great feature is it takes a lot of your IV calculation guesswork out of it, because it has a built-in little calculator in it that you can plug in your pieces of data, and it will do the math for you. So it can be very, very helpful. So setting a drip rate, we're going to adjust the flow based off of the number of drops that we see. So if you will take a look back again on 294 in your text, the IV bag picture, upper right corner there, it talks about the flow regulator. Often gets called the roller clamp, but the roller clamp, if you dial it up, it speeds up. If you dial it down, it slows down. So up towards the bag speeds it up, down towards the patient slows it down. So we're going to watch the drips in the drip chamber, and if they're going too fast, we just back down a little bit. Going too slow, we just push it up just a little bit. And again, I said IV infusion pumps can be enormous help when you are trying to precisely infuse fluids. And to test the accuracy of your math skills, you should choose a calculator. Most services have an El Cheapo $1 Dollar General, Dollar Tree, Walmart calculator velcroed to the wall in their trucks. You don't need anything fancy. It needs to add, subtract, multiply, and divide. So you don't need a scientific calculator. You don't need a laptop or a supercomputer. Anything that you might already have in your basic phone or your smartphone will work just fine. I prefer to have it when people can actually do the math if they have to, but when we can, we'll use that drug calculator or the electronic device to assist us in making those calculations to improve our accuracy.